Dear participants, dear students and young researchers, distinguished speakers and guests, respected colleagues, good morning everyone. Today is another wonderful day as we begin our second summer research school on gravitational waves, new challenges and opportunities in the series of Frontier of Science. First of all, please allow me to express my sincere gratitude to all of you for coming, for our distinguished speakers, for accepting our invitation to come and give lectures at the school. The school is a very meaningful event for us, as it marks a new stage in revitalization of TÜBİTAK Research Institute for Fundamental Sciences, TBAE. It brings together motivated students and young researchers and world-class experts in the field, thereby paving the way for producing a cutting-edge knowledge for the country and for the world. More than 400 years ago, Galilei pointed his telescope toward the sky and discovered 4 satellites of Jupiter and the phases of Venus that had never been known before in exploration of the world systems. Almost 150 years ago, Maxwell formulated the mathematical theory of electromagnetism and predicted the existence of electromagnetic waves and proved the electromagnetic nature of light. In subsequent developments, the practical application of these discoveries and exploration of the universe and structure of matter in all bands of electromagnetic waves drastically changed the world and the human life. Gravitational waves were predicted by Einstein more than a century ago within his theory of general relativity. The recent detection of gravitational waves from merging binary black holes and binary neutron stars can be considered as one of greatest triumphs of pure theoretical reasoning and mathematical construction of all times. Gravitational waves carry the signatures of the dark side of warp space-time, thus opening a new window on the exploration of the universe. The detection of gravitational waves also represents frontier technological challenges, such as advanced laser interferometers, detectors and quantum metrology, information and control system, modeling and simulation of violent events in the universe. The research summer school is devoted to this newly emerging and fascinating area of modern science. It is my great pleasure to introduce you our first speaker, the world-class expert in the field, Professor Scott Hughes from the Massachusetts Institute of Technology of United States. Professor Hughes' research interests cover a wide topics in astrophysics and general relativity, focusing in particular on black holes and gravitational wave sources. Professor Hughes was an undergraduate at Cornell University. Then he received his PhD in physics from the California Institute of Technology, working with Professor Kip Thorne, the Nobel Prize winner for detection of gravitational waves. Later on, the world line of Professor Hughes passed through many universities, among them University of Illinois, again Caltech, the University of California, Santa Barbara, and finally he became a full professor at MIT. Please join me to welcome Professor Hughes warmly and invite him to begin his lecture.
Thank you very much. All right. After an introduction like that, I hope my lecture is not a letdown. That was wonderful. Thank you. It really is truly a privilege to be here today, to be able to begin to inaugurate this series of lectures on gravitational wave physics. As Professor Alikram says in his introduction, we really have, over the past couple years, embarked on an amazing new epoch in observing the dark and dynamical universe using the gravitational wave detectors, which have actually been under development for quite a while, as I will discuss in my public lecture this evening, but have recently reached the sensitivity where they can begin making these different detections, which are now, at last, producing what can truly be called gravitational wave astronomy. You know, my PhD thesis, which was written over 20 years ago, had as the title Gravitational Wave Astronomy. And I remember when I interviewed for faculty positions, people would sort of say, doesn't that seem a little ambitious? And I always would say, yes, it does. But it's been achieved. So let me tell you what my plan is for these lectures. My goal is to describe how it is that gravitational waves arise and how they encode astronomical information about the sources that produce them. And this will complement certain aspects of my colleagues who will be speaking. So Badri Krishnan is going to go into more detail in several aspects of the measurement process and ways in which this information is encoded into the waveforms. My colleague Lucian Rezzola, who has not yet arrived, is going to talk in a lot more detail about some of the techniques that we use to develop models for the waveforms and to relate the waveforms to the characteristics of the binaries that produce them. And my dear friend and colleague from MIT, Nurgis Mavlavala, will describe to you in great detail the way in which these detectors actually work and how it is that this amazing technical achievement can actually be made. So as far as my personal 4 lectures are going to go, this first one, which will last a little less than an hour, is going to review the basic nature of gravitational waves and to discuss the 4 different frequency bands in which we characterize gravitational wave measurement and the ways in which we measure and in some cases attempt to measure gravitational waves in these bands. My second lecture for today will go through the basics of wave generation. So I'm going to talk about how it is, focusing for the most part on binary inspiral, the case in which we have 2 stars or star-like objects in orbit about one another, how it is that we take the equations of general relativity and produce our predictions for the gravitational waves that they produce. I am then going to give a lecture which will have a little bit of overlap with Professor Mavlavala's lecture, in which I'm going to describe how it is that gravitational waves imprint themselves on matter, and in particular how they imprint themselves on the detectors that we wish to use to measure these. One of the outcomes of this, which is going to feed very closely to Professor Mavlavala's talk, is understanding the way in which noise in these detectors, which is inevitably present whenever you try to do a real measurement, interferes with the ability to measure these waveforms, and why it is we need good models of these things, why we need to understand wave generation so well in order to measure these waves in realistic detectors. And then in my final lecture, which will be tomorrow, I'm going to talk about the science that we are doing with these. This is one I'm actually going to make some adjustments to, and I think I'm going to also talk a little bit about some of the more advanced topics that are currently being done in order to prepare for upcoming instruments, in particular the space-based gravitational wave detectors that are currently being developed and that I am optimistic will launch and begin making measurements before I retire. I'd say that with about 50-50 confidence. You know, perhaps it'll be my students who get to do the data. But when you work with space-based projects, it pays to be patient. So let me begin the lecture proper. So if you want to convince someone who is not a physicist why it is that gravitational waves must exist, the key thing to remember is that in Newtonian gravity, so the gravity that was the foundation for our understanding of how objects fall to Earth and how planets orbit stars, how that was formulated for hundreds of years, all information about gravity in Newtonian framework is transmitted instantaneously. So if I have 2 objects, let's call them stars, that are separated by a very large distance, and one of them moves, Newtonian gravity claims that the information about this star's new position is instantaneously known to the red star over here. That is contradicted by the fact that we know information can travel no faster than the speed of light. General relativity provides a framework. So Einstein's theory of relativity builds into it the idea that there is a maximum speed limit to the propagation of all information. And general relativity essentially just provides a framework for incorporating all of the principles of relativity into a theory of gravity. And so what I'm going to do in this lecture is go through a description of fairly superficial, and we'll go into more detail in my next lecture, a description of how it is that radiation is encoded in general relativity. So I'm going to begin with a useful analog. So let's go into and remind ourselves how radiation emerges in Maxwell's equations. That is a very useful analog because it gives us a complete linear classical relativistic field theory. So this is very useful for introducing and reviewing the concepts and methods that I'm going to want to use, many of which carry over to gravity. But I should always caution you that this is just an analogy, and many of these steps need to be justified more rigorously. I will not have time to do the most rigorous justification in these lectures, but it has been done, mostly because general relativity is, of course, a nonlinear theory. Okay, and so if you use the electromagnetic intuition a little too much, misleading things can emerge. And so I will be careful to highlight where it's appropriate and where there are additional steps that must be done more carefully. So I'm going to begin with what everyone hopefully learned in an undergraduate physics class at some point, the Maxwell's equations. So these four equations, plus a equation expressing conservation of source, which is actually encoded in this, they give a complete description of the electric and magnetic fields and how they relate to charges and currents in classical physics. I want to put this into a different form of notation, which is a little more convenient for introducing the language I want to use to generalize to gravity. And so I'm going to take my electric and magnetic fields, written in vector format here, break them into components and encode them in a tensor. Okay, so this Faraday tensor completely describes both the electric and magnetic fields. And in the framework of this mathematical object, those four Maxwell's equations are expressed by these equations here. So you have all probably seen this, but just because I believe will these slides be made available, by the way? Will these be posted to a website somewhere or something like that? Great. So for completeness, I just want to review then the notation for these. So I'm using the Einstein summation convention, and throughout this, the next couple slides, I will always be raising and lowering various indices using the metric of special relativity. Okay? So I put this all up just so that for those who read these later, you can find what notation I'm assuming. Okay, so I'm expressing my electric and magnetic fields using this tensor F mu nu, the Faraday tensor. This is an antisymmetric tensor, and that means that I can always construct it from a potential, a one-index potential, like so. This form guarantees that the tensor that arises from this thing will be antisymmetric. Now, we have freedom from this formulation to adjust the potential using a gauge transformation. So given the existence of some vector potential A mu, I can change it by the gradient of any scalar field. Doing so leaves this completely unchanged. Okay? So the fields are invariant to this gauge choice. And this is great. I like to, when I am teaching undergraduate physics, I like to tell people that this essentially it allows physicists to do what we love to do, which is to be lazy. Okay, this allows us to reformulate our equations in a way that makes it as easy to solve them as possible, or as convenient to solve them as possible. So what we are going to do is we're going to adjust things so that this potential is divergence free. Okay, so I'm going to choose my lambda. If I have some particular vector potential and I choose lambda such that it satisfies this equation, then I am guaranteed that my new vector potential will have no divergence. And then my Maxwell's equations can be rewritten in a form that only depends on the potential, like so, where this is the wave operator. And so essentially it's saying that the wave operator on my potential is, up to a constant, just the electromagnetic source. What's wonderful about that is that this can then be solved using the method of Green's functions. So for those of you who would like a quick review of this, the basic idea of the Green's function method is that if I have a linear differential operator acting on a field, and that equals a source, what we do is we replace this source with a Dirac delta function, or with actually several Dirac delta functions. And I'm going to assert that some function g exists that solves this equation when my source is just this point-like delta function. If that source exists, then we trivially have that the source is given by integrating itself over the delta functions. And so by linearity, I can get my solution, the field for a given source, by just integrating that Green's function against the source. The proof of this is just, oops, actually it's already here. Just take this operator D and apply it to this F. And when you work through here, the fact that D only acts on the unprimed coordinates means it will ignore your source in this under the integral. It will hit the Green's function. It will pull out the delta functions. And you will just recover your original equation. So the reason I'm going through all this is because when your equation has this wave operator form, we can do the other thing which physicists love to do, which is look up the answer that someone else has figured out. Okay, so the Green's function for a wave operator can be found in any number of textbooks on classical electrodynamics. So given that your wave operator is, your differential operator is the wave operator, set the source equal to the Dirac delta function, this is what your source, your Green's function turns out to be. So that means we can immediately write down an exact solution for our potential. It's just given by integrating the source evaluated at retarded time. So remember, I've set the speed of light equal to 1 here. And so what this is saying is, if I want to know the vector potential at some position x at time t, I integrate the source over its spatial extent, and I evaluate the time taking into account the travel time that light takes to go from the event currently under the integral to the point where I am now evaluating for my field. And I also divide by 1 over the magnitude of the distance. So with that review behind us, and I'm going to take advantage of that review when I step from electricity and magnetism to gravity in a few moments, what I want to do is find a form of my A mu that is appropriate in a radiation zone that is far from the source. So the way I'm going to do this is I'm going to take both my potential and my source, and I'm going to expand them in Fourier modes. I'm going to assert that A mu can be written as A mu as a function of x times essentially a plane wave. Strictly speaking, there should be a sum over different modes in here, or an integral over omega. I just want to leave that out for notational clarity. Same thing for my source. Okay, it's going to look like a function only of space times a simple plane wave expansion in time. Plugging this into my solution, I get a nice simple form that only basically the e to the minus I omega t cancels out on both sides. So this tells me how the spatial dependence of my field depends on an integral over the spatial dependence of my source. Okay, so I've introduced here now k, which in the units I'm using is the wave number for the radiation. Now, to make further progress, everything I've done so far, I've not introduced any kind of expansion or made any approximation. What I would like to do now is find a solution that's appropriate in what I will call the radiation zone, a region that is far from the source. And so what I'm going to do is imagine that I'm only interested in the solution at distances much larger than 1 over the wave number. So let me make a couple of definitions. I'm going to call the magnitude of x, so that's the distance from sort of the center of where my source is to where I am measuring my field. I'm going to call n hat a direction vector that points from that point to where I'm measuring the field. Okay, and I'm going to introduce a fairly standard expansion of this factor, which is the Euclidean distance between where I am measuring, where the current contribution to this field comes from and where I'm measuring it. Okay, so I'm throwing all this in here. So far, everything is, I hope, standard. There we go. Okay, so using the fact that when I expand this, the most important term looks like so. To order 1 over r, this exact solution becomes a form that looks like this. And so I get something that looks like a plane wave in space with a 1 over r form here, and an integral over this spatial dependence of my source and something that looks like, notice what I'm doing here is I'm integrating over the source and I've got this direction vector appearing in there. I'm going to introduce now an expansion of this exponential. Okay, so replacing that like so, this turns into now an infinite sum, simply just the Maclaurin expansion of e to the ix going on here. Okay, now, what I want to do next is consider this term for every one of the, I want to consider this for every one of the values of b that appear under this sum. That's going to introduce a multipolar expansion of this charge distribution. So let's begin with b equals 0. So I'm going to actually go back to the original exact solution, and I'm going to do a little expansion of this thing. So my exact solution looked like so. Introducing my various approximations, I can turn this integral, this exact solution for this thing, into a form that looks like this. And the component J0 of this current that appears here, so this is just, I'm just doing the time component of my vector potential. This is nothing more than the charge density. So I can integrate that up. I integrate charge density over volume. I get charge. But that charge is conserved. It's a constant. So what this tells me is that the time-like component of the vector potential is nothing more than Q over R. It's the Coulomb potential. Probably the most complicated derivation of the Coulomb potential you've ever seen. Okay? But I wanted to throw it out there so that we can see the way this emerges. Let's look at the other pieces of this vector potential. So again, doing this for b equals 0, I get something where I'm essentially just doing a spatial integral over the other components of my source. A theorem tells me that this integral can be rewritten as, I can rewrite it as the divergence of that source against essentially the spatial extent of the source itself. This is a very useful result because I can take advantage of the fact, so that means that I just turned my integral for the spatial components of this potential into this form. My current is related to the charge by the continuity equation. Okay, so I can relate d rho dt to the spatial divergence like so. Now I'm going to introduce Fourier modes, and what I'm going to do is expand rho. I'm going to assume that it has the form some spatial function e to the minus I omega t. This equation turns into something like so. And what I wind up with is that my vector potential looks like an integral of the spatial extent of the source times the charge distribution. That, by definition, is the dipole moment. So what I've just shown you is that at this level of approximation, the spatial components of these things look like minus I omega times the dipole moment of the source. But remember, I have introduced a Fourier expansion in time. So minus I omega is nothing more than the time derivative. So we put all this together, and what I just showed you is that the spatial pieces of this thing that falls off as 1 over r, and it's related to the first time derivative of my source's dipole moment. So I've just done for you, in about a little more than 15 minutes, what usually takes about half of a semester in an undergraduate electrodynamics class. I just did the first leading solution of radiation in electricity and magnetism. We can keep going, okay? I won't do these explicitly, but the basic idea is go back to this formulation of the equations here and examine ever-increasing values of the index and the expansion, the b. So b equals 0 just gave us the leading Coulomb piece and the first dipole piece that gives us electromagnetic radiation. And as you go to higher and higher b, what you will find is that each term defines a higher multipole contribution to the field far from the source. These terms will divide into electric and magnetic moments. So I'm going to sort of write it heuristically. When you go through and you work out the way all this is going to work, you'll find that each contribution to potential looks like the Lth contribution, looks like L time derivatives of these moments, which I will label E sub L and M sub L. E sub L is an electric charge moment. It essentially looks like L powers of length integrated over the charge. And the m sub L, those are magnetic moments. They are moments of the current distribution. And they look something like, schematically, L powers of length times the velocity with which charge is moving around inside your source, integrated over the charge distribution. What's going to be important, especially as I go to gravity, is what we can take from this is some intuition for how all these different terms contribute to the radiation that is measured far away. So let's imagine I have some bound source. Let's say it's me. Okay? I have a total charge Q. I have internal speeds as I wiggle around here, which I will call V. And I have a size that I will call L. As I go and evaluate these moments integrating over my source as I wiggle around up here, what you're going to find is that the electric moments will have a form that is roughly the total amount of charge in that source times something that looks like the size to the Lth power. And when I take L derivatives of this thing, it will be the amount of charge in the source times something that looks like the internal velocities suppressed by V to the L. And bear in mind, I typically work in units where the speed of light is 1, so putting that back in here, it's saying that the Lth moment looks like the internal velocities divided by c to the Lth power times the charge distribution over my source. And when I do the same thing for my magnetic moments, I get a very similar scaling, but because the magnetic moments involve an additional factor of the internal velocities, they will be suppressed by an additional factor of V over c. So this, in a nutshell, is how electromagnetic radiation works. So if I want you to take something away from this, here is sort of the final solution. We find that our radiation has electric and magnetic multipole contributions. This is the form of my electric contributions. This is the form of my magnetic contributions. And the key thing that we find is that the L plus 1 moment of electric is a factor of V over C smaller than the E of L. And at a given value of L, M sub L is a factor of V over C smaller than E sub L. The leading radiation comes from L equals 1. An important point is that the monopole cannot radiate. And that fundamentally came down from the fact that we got that solution by imposing charge conservation. All right. Let's switch from E and M to gravity. That's why we're here. So the analogous concepts which we're going to use, we don't actually have a gravitational field so much in general relativity as you have a tensor, which I will describe in more detail later, which describes the curvature of space-time. This is going to, which we'll see, give us a precise description of tidal forces. The role of the potential is played by the metric of space-time, and what it does is it tells us what the distance between two events in space-time is. So if you give me the coordinates of this point in space and time, the coordinates of that point in space and time, and you tell me the space-time metric, which sets the geometry of the manifold that those points live in, I can get the distance by essentially integrating up a formula based on this. I'm going to work in units for this lecture in which every one of my coordinates has dimensions of length, in which case my metric is dimensionless. So we're going to begin by imagining that gravity is weak. Okay? Weak for us means essentially not much stronger than, say, the truth is Earth's gravity is very weak. Okay? In many cases, the gravity on the surface of a white dwarf star is very weak. Okay? It would crush us flat, but it's weak for our purposes. So when I say strong later on, that's going to generally mean that I'm within a couple of gravitational radii of a black hole. So for us, since we're going to assume gravity being weak, our space-time metric will be close to the space-time metric of special relativity. So this is a quantity which in these coordinates is -1 in the time component and then 1 on the diagonal, 0 everywhere else. All of the interesting functional dependence is going to be hidden in this h, okay? And this perturbation to the flat space-time will include all the properties of gravity, including radiation. So what's particularly nice, and I will just develop this in more detail in the lecture that follows this one, is that this HAB, I can think of it as a potential. It is governed by an equation that's very similar to the equation that governs the vector potential of electricity and magnetism. There are some important differences, obviously, but in terms of its mathematical structure, it's sufficiently similar that I can borrow many of the techniques from electrodynamics and just apply them and carry forward with my life. So when we go through, so bearing that in mind, and like I said, I will go through this in more detail in my next lecture, we expect to have two contributions to the H that arises here. There'll be sort of a gravito-electric one, which arises, it has sort of a structure to it, which is similar to the potential we derived for electric charges. And it's going to depend on a set of multipole moments that look something like L powers of length integrated over a mass and energy density. And I'll expect there to be a gravitomagnetic contribution to the field, which will look like L powers of length integrated over internal source speeds times the mass and energy density. Okay, so we're going to introduce two important families of multipole moments, mass moments and current moments. And so mass moments, again, if we sort of think of me as the source of gravity here, the mass moments are what you get if you just integrate over the distribution of my body at every moment in time. And the current moments are those you get where you take into account my hands waving, as one is wont to do in a physics lecture. All right, bear in mind, I have defined my coordinates so that my metric should be dimensionless. If we go back and you look at this, these are not dimensionless quantities. So what we need to do is multiply all of my masses by g over c squared, multiply all powers of time by a c, and divide all velocities by c. That will give us, that will convert those heuristic formulas I wrote down on the previous page to slightly less heuristic formulas that allow me to understand how the contributions to this space-time potential scale with masses and speeds and sizes and things like that. So I'm going to go through, so what I'm basically doing is I want to just look at this form for different values of L. So when you look at L equals 0, there's only one contribution. It tells you that there is a monopole contribution to the gravitational interaction. That modulo a factor of g over c squared is just the mass of the system divided by distance. That's just the Newtonian potential, okay? We knew this 400 years ago. It must be, the m that appears here must be constant, okay? A system's mass and energy has to be conserved. So this is a perfectly valid solution, but it's not radiation. And indeed, when you solve the Einstein field equation, especially when you do it in the linearized limit, this pops right up, and it's how we show that general relativity incorporates the Newtonian limit, okay? The fact that it pulls out the Newtonian potential makes perfect sense. Let's go to the next one up. So in electricity and magnetism, I found a dipole moment, and that ended up giving me radiation. Well, my first dipole moment that I find when I go through this form for my gravitational potential, it ends up looking like 1 over r, g over m cubed, times the first derivative of the first mass moment. So that first mass moment, you know, if this rho were charge, this would be the charge dipole moment. So this is more like a mass dipole moment. What the heck is a mass dipole moment? Well, in fact, it's something that's not actually very meaningful, but its derivative is. Its derivative is just the total momentum of the system. Now, you're all good physicists, so you know that that's not uniquely defined, okay? Right now, you all, to me, have momentum 0. Now, you all have momentum a little bit different from 0, okay? I can change your momentum, at least as far as I'm concerned, by just walking back and forth. That's gauge, okay? And so what this is saying is that this is a term that it exists. When I solve the field equations, I get terms like this, but when I interpret them, they depend on the coordinate system I use to write down my solution. Cannot be radiation. In this case, it turns out there is another kind of dipole that enters that's really interesting, which is a dipole of, if we look at this, it's essentially the dipole moment of internal velocities times the mass distribution. This actually, if you look at it and think about what this means, dimensionally, it looks just like angular momentum. And in fact, if you do a more careful analysis than I am doing here, terms of this form enter, and they are related to the time variation of the angular momentum of your distribution of masses. Global angular momentum conservation means that has to be 0. So conservation principles protect against this being a radiative solution. So the first moment that is not protected by a conservation principle and is not simply a pure gauge is what I get when I look at the second derivative of 2 moments of my mass distribution. So I end up with a form where there is a g over c to the 4th times 2 moments here. This is a quadrupole moment of the mass distribution. Nothing prevents this from being radiative. And so simply by virtue of the fact that it is not protected by a symmetry or a conservation law, we conclude that the quadrupole moment has variations that can produce gravitational radiation. One point which we'll come back to in just a moment is, notice when I actually work this guy out, there's a coupling constant. Newton's gravitational constant, which is a pretty small number, divided by the speed of light, a big number, to the 4th power, making it a really big number. And so we're going to find that it takes a lot of change of mass quadrupole moment to get any significant amount of radiation out. So what exactly is this radiation? We'll talk about this in a little bit more quantitative detail now, but what I would like to stress is that in general relativity, the fundamental gravitational field is the curvature tensor, which tells me about tides. And so we expect this gravitational wave to manifest itself as an oscillating tidal field. If I had a ring of test masses, then I would find when a gravitational wave passes through them that they would sort of be alternately stretched, the geometry of that ring would alternately stretch and squeeze. And because of its tidal nature, I can define fundamental polarization axes, which sort of look like a plus configuration if I arrange it according to some preferred coordinates, and a cross configuration across to another one. That metric, that amplitude h, which describes the metric itself that I've been framing everything in terms of, that actually ends up being, to within a factor of order unity, nothing more than the strain that each individual mass goes over. So if the separation between these two masses is L, then the delta L over which they oscillate is divided by L is just the h that I've been calculating. That also tells me that since my g over c to the 4th means h is a small number, I expect my delta L to be a small number. The amount by which I'm sketching it here is perhaps a little exaggerated. All right, so let's actually calculate what the magnitude would be. So I'm going to use this formula that I did earlier and throw in a little bit of dimensional analysis to figure out what the size of this thing will be. So my radiative h looks like g over c to the 4th, 1 over distance, and then 2 time derivatives of this mass quadrupole moment. So when you actually propagate your 2 time derivatives underneath this thing, to within a factor of order unity, this looks something like the total mass of your source times a square of something like the internal velocities associated with the source's motion. Now, what this twiddle here actually means depends in detail on the geometry of your source, exactly how the dynamics are manifesting themselves. If I have 2 stars orbiting each other in a circle, then this formula turns out to be accurate and the coefficient is of order 1. If I have me dancing around just making lots of wiggly motions, this ends up being suppressed because the angular distribution of my internal velocities is very, very random. And this coefficient here might be more like a part in 1,000. Okay? Let's imagine we're lucky and we give us a source where the coefficient is on the order of 1. Then mv squared, that's kinetic energy, up to a 1/2. But I'm doing things where 1/2 equals 1 to this degree of approximation. And so this time derivative of the quadrupole moment looks something like the kinetic energy associated with internal motions of my source. So let's imagine that my source has, its total kinetic energy is on the order of the mass of the sun times the speed of light squared. Why not? Let's imagine it's about 100 megaparsecs away. And then let's throw in this g over c to the fourth. When you do this, this gives us the estimate that the typical magnitude of this radiation is a part in 10 to the 21 or a part in 10 to the 22. Okay? This is the bit that when people first started thinking about gravitational wave detection and they realized what the experimental challenge was, which was actually approximately around the time I was born, is when people started doing this. And I was born in 1971. They sort of looked at this and went, huh, maybe not today. This immediately leads to a very difficult experimental challenge, and we'll return to how one overcomes that in a later lecture. Now, this is a tiny effect in terms of what we want to measure in terms of the shift of these masses here. It's due to the fact that gravity is the weakest of the four fundamental forces. And what's interesting is that although that strain, the thing you are directly trying to measure, is tiny, the amount of energy that it carries can be enormous. So again, let me introduce an electromagnetic analogy. So in electrodynamics, if I want to know the total amount of radiation carried by an electromagnetic wave, I go to the Poynting vector. And my dEdt is given by integrating the Poynting vector over a closed surface. And I find that it looks something like the square of the time derivative of that electromagnetic potential that I wrote down earlier. We want to do something similar for gravitational waves. This is where the analogy to electrodynamics can be misleading and can be dangerous. We cannot localize gravity in general relativity. Okay? One can always imagine choosing a coordinate system in which this is what the principle of equivalence is all about. You can always choose a coordinate system such that at a particular location there is no gravity, even if there are very strong gravitational waves present. Physically, it means that you're doing your analysis in a freely falling reference frame. So in order to actually define a notion of energy carried by gravitational waves, you have to either take advantage of the fact that the waves have some very large extent, and so the non-local nature of the radiation comes into play, or you work with a pseudotensor, which, for those of you who have studied the subject, means it has lost some of the invariance properties that make tensors so nice, but nonetheless is well-defined, at least within a certain specific calculation. I'll talk about both of these in a bit more detail in my next lecture. So we go and we do this. And what we essentially find, once we have made this a little bit more rigorous, is that the amount of energy carried by my gravitational waves, in a very similar form, it looks like the time derivative of my potential, which in this case is the strain h squared. Notice that here, my factors of c and g come in such a way that it actually makes the numbers bigger. And this is telling us that even if my h is tiny, the amount of energy they carry can be enormous. Okay, so if I talk about the kind of sources that LIGO is now measuring, LIGO and Virgo and other detectors around the world are now measuring, your strain might be a part in 10 to the 22, the source might be, say, 100 megaparsecs away, and at some moment it might be periodic, have a frequency of 100 hertz. That source will, at that moment, be radiating with 10 to the 20 times the amount of energy put out by the sun. So these are incredibly energetic objects, but which, thanks to the weakness of gravity, are really difficult to measure. So what we then expect is that if an object is going to be an interesting gravitational wave source, it needs to have a very highly variable mass quadrupole moment. We need a lot of mass moving very quickly. To make it move very quickly, and by very quickly, I mean near the speed of light, it has to be compact. You can only get a lot of mass moving at speeds that are comparable to the speed of light if it's so small that it can actually turn itself around and get accelerations that allow it to move that quickly. And so that basically tells us that the ideal sources are going to be black holes and neutron stars. There is hope that we will get things that involve stellar core collapse coming in and becoming interesting sources. These events are relatively rare. And an issue is that when you have a stellar core collapse, means essentially the engine that powers a supernova. problem is that a lot of the masses are moving in a very stochastic kind of random mixed up way when that happens. And so although you do have heavy masses moving at high speeds, they may not be super coherent. And so getting a waveform out of them that we can recognize against noise, that's a challenge. And it may be, and this is one of the things that drives a lot of people to think about this field, the dynamics of the early universe could be something that produces strong and interesting gravitational radiation. But here, you're now getting into the realm of theoretical speculation and stuff that's a lot of fun, but really hard to design an algorithm to try to measure it in your instruments. So let me wrap up this first lecture over the next 10 or so minutes by speaking about the different sources and the way that they overlap with bands in which we measure them. So when we speak about gravitational wave measurement, professionals in the field usually focus on 4 distinct frequency bands. The ones where all the discoveries have come in the past couple years are in what is known as the high frequency band, which ranges at the low end from a couple of hertz up to about 10,000 hertz. I'll talk about what sets those limits and what sources are in them in just a few moments. We also think about a low frequency band, where the low frequency is 10 to the minus 5 hertz. That is the inverse of several hours. And it goes up to about this here. These are targets for space-based gravitational wave detectors, in particular the LISA spacecraft, the LISA constellation of spacecraft, which is being designed for a launch, like I said, hopefully before I retire. This is the band that it would target. Active right now are people who are searching for waves in what's called the very low frequency band, where your limits go from about a nanohertz, 10 to the minus 9 hertz, up to a fraction of a microhertz, about 10 to the minus 7 hertz. The inverse, this is often best expressed actually in terms of the inverse of the frequency, the periods that you are looking at. So this is a period, the inverse of a microhertz is on the order of a couple of days. And the inverse of this is on the order of a couple of decades. Hard to look for a periodicity on that thing. I'll describe what sets the limits, why this band is interesting in a few minutes. And then finally, the ultra low frequency band, if I were to write this in terms of times, it would be ridiculous. So I'm going to write it in terms of wavelengths instead. This is radiation whose wavelength ranges at the large end from essentially the size of the universe, the inverse Hubble scale, to a factor of several micro inverse Hubble scales. So this is radiation that leaves an imprint on the cosmic microwave background. Right now, there are very active programs searching for radiation in these bands. This is being actively measured in this band, and the mission that we'll measure here is under development. So my last several minutes of this lecture, let me go through these different bands. So when I look at the high frequency band, like I said, the low end of that is roughly a hertz. The reason is that if you try to go below about a hertz in any terrestrial detector, noise will kill you. Okay? Even if you can make an object that is completely and perfectly isolated from every vibrational motion on Earth, you cannot isolate it from gravitational oscillations in the Earth itself. As part of my PhD thesis, I did an analysis with Kip Thorne of gravitational coupling of vibrations in the Earth's surface to the test masses in the LIGO detectors. And this is actually what drives this idea that you cannot go below about 1 hertz. I mean, it's simply the fact that the Earth is vibrating. That vibrating Earth causes the density of the Earth to fluctuate a little bit as seismic waves pass by. And gravitational coupling of those seismic waves to gravitational wave detectors ultimately sets your sensitivity here. Interestingly, there are some geophysicists who saw that and go, ooh, that's interesting. And so what they want to do is make detectors that are sensitive significantly below 1 hertz in order to measure the large-scale motions of masses in the center of the Earth, which is cool, but it's not gravitational waves. The high end of this scale is set roughly by the idea that you are measuring up to something like 1 over the shortest time scale that's likely to be associated with any source. A little bit more carefully, the maximum frequency that you expect something to radiate at is on the order of, modulo factor of 2 pi, internal speed of your source divided by the size of the source. if you require that your internal speed be less than the speed of light, you require that your source be a black hole or larger, then that drives you to a rough estimate that the maximum frequency is about c cubed over gm for a source with mass m. And for a solar mass, that turns out to be 10,000 hertz. So this is how the sensitivity of LIGO was determined, was essentially by these two bands. So the two detectors in the United States that are measuring this right now are the LIGO detectors. You'll hear a lot more about these in one of my lectures tomorrow, and an extremely greater wealth of detail from Nuhbalaoğlu's talk a little later this week. So these are the ones in Livingston, Louisiana, and Hanford, Washington. The only thing which I'll mention right now is recall that the amount of length shift that one measures from a gravitational wave is proportional to the separation between two test masses. So each of these arms is 4 kilometers long, so it's 4 kilometers of evacuated vacuum. There is also a similar setup in Virgo, in Pisa, Italy, run by a French and Italian collaboration. And several other instruments are online. I don't have a slide for this at the moment. I should have added one. But a similar setup is about to start running in a mine in Japan, in the Kamioka mine, where there's also a neutrino detector called the Kagra detector. Here is what their sensitivity looked like as of just a little under 2 years ago. So this is right before these guys measured the first binary neutron star. And you can see that, ignore the spikes for just a moment, you can see that LIGO has a peak sensitivity that goes down to about a little less than a strain of 10 to the minus 23. You have to be a little bit careful because in these units you also want to multiply by a factor that looks like the square root of the frequency because you integrate over a broad band, and there's some signal analysis details which Badri will talk a lot more about and that I will mention briefly in one of my lectures tomorrow. But this sort of tells you that these are sensitive to waves at about the 10 to the minus 22 level at their peak. Virgo was at this time a factor of half an order of magnitude or so less sensitive. And you'll note Livingston is a little bit less noisy at low frequencies than at Hanford. There's a little bit of a rivalry between the two sites about which one can do better there. At any rate, there's, this is active experimental work to improve these various things. Let's go into space. So in the low frequency band, as I mentioned, we try to make measurements ranging from about 10 to the minus 5 hertz up to about a hertz. Now that low end, that is set by, it's roughly 1 over the longest time over which we believe we can control the noise environment of a spacecraft. So if we can control the noise environment for a couple of hours, that means that we can get good sensitivity down to about 10 to the minus 5 hertz. Okay, that's actually a little bit of an open question, how low these things can actually go. One issue is that when you are flying a spacecraft, the agencies give you a lot of money, and they want you to demonstrate that you can do what you say you can do. We can only test these things on the ground, though. And on the ground, you're in the thermal environment of Earth, and guess what? The sun rises and sets. And so the thermal environment varies with a period of about 12 hours. And so that makes it difficult to test things more than on this kind of a time scale. So we might be able to go lower than that, but we can't tell our agencies credibly that we can, so that's the official lower limit. On the high end, we believe we can go up to almost 1 hertz, and what ends up setting the sensitivity here is the ability to count photons as you go back, as they move back and forth between the spacecraft, and also the fact that these spacecraft are in an orbit that lags behind the Earth by several tens of millions of kilometers, and just downloading the data is a little bit challenging, okay? And so, if you sample your data stream more frequency than about 1 hertz, you eventually overwhelm your ability to download data to the Earth. So this is, I'm showing you a sketch here of the Laser Interferometer Space Antenna, a mission that is now being led by the European Space Agency. It used to be a joint mission of ESA and NASA, but then NASA kind of went insane, and so we had to pull out, but we're getting better. This is a little bit of an out-of-date sketch. The noise sensitivity has a shape that's reminiscent of what you see in the LIGO detectors. Sort of goes up at low frequencies, goes up at high frequencies. But what's particularly interesting here is that there's a really noisy patch in the middle which has nothing to do with the instrument. These are actually all the binary stars in our galaxy, which are so loud that they actually turn into noise if what you want to measure are things involving black holes. As someone who's been in the field now for probably about 25 years, the idea that astrophysics provides the noise instead of my instrument providing the noise is pretty cool. So I will talk a little bit more about the science we get from these things in one of the future lectures. Now, in the very low frequency band, this was one where we measure things where on the long end, the period is on the order of several decades. What sets that is that we have been observing pulsars for several decades. So we have a data stream that's about 30, 35 years long. And so in principle, if you dig into that data well enough, you should be able to find something periodic with a period on the order of a decade or so. And then at the short end, it is roughly 1/3 months, which has to do with how often you observe the pulsars that you are studying and various schemes that you use to try to beat down noise in your detection measurement. And the basic idea here is that you are going to use very stable millisecond pulsars as clocks. So if I have a gravitational wave source and I have a millisecond pulsar over here that I'm measuring on Earth, as the radiation field passes between me and the pulsar, the arrival time of my pulses will oscillate in a coherent fashion due to the wave, the electromagnetic wave propagating through the field of the gravitational wave. So the basic idea here is that you can use a really accurate clock as a gravitational wave detector, and nature gives us some of the most amazing clocks scattered all over the sky. And so there is, at the present, a program to go and monitor many, many pulsars to try to look for this sort of influence, but it's hard. Finally, the ultra-low frequency band. Basic idea here is you're looking at things which range in wavelength from a sky that's on the order of the size of the universe up to the sort of smallest scale that we can resolve very well in the cosmic microwave background. The source from this would be primordial ground state fluctuations of space-time itself, then amplified perhaps by inflation. Alan Guth is at my institution at MIT, so I'm required to say it's inflation, but let's keep an open mind here. If this were the case, it would leave an imprint on the cosmic microwave background that uniquely affects the polarization of the photons that come from the cosmic microwave background. I can answer questions about this, but this is not something I work on myself, and so I'll be happy to try to answer any questions, but we're close to the limits of my knowledge of this. So I will wrap up this first lecture, and we'll take a short break, I believe. The main thing which I really want to emphasize is the idea that the radiation enforces the rule that changes propagate no faster than the speed of light. The radiation is at leading order quadrupolar because monopole and dipole moments cannot radiate. It's weak, but nonetheless, they carry an enormous amount of energy. And so this weakness, the energetics is just related to the fact that you're looking at processes that involve ultra-relativistic, really massive things. But because gravity is the weakest fundamental force, they become very hard to measure. So I believe we have a little time in the schedule for a break, so I will stop here, and then after a little time off, I'll get into more detail about sources in my second lecture. Thank you. So happy to take questions while we go get ready for the break, just as long as I can get some water. Yeah.
This gravitational waves from the Big Bang is out of question at the moment or not?
Is this an active question?
I mean, like they retracted whatever they claimed.
So, yes, there was a claim a number of years ago. So here's where I'm now going to start stepping into slightly dangerous territory, but I will do my best. When one analyzes the polarization of the cosmic microwave background, the vector field that describes polarization comes in two flavors, depending on its handedness. So there is one part that is of even parity, another part that is of odd parity. So the bit that's even parity kind of looks like the gradient of a scalar field. The bit that's odd parity looks like the curl of a vector field. In terms of what fundamentally produces it, simple mass fluctuations will produce both even and odd parity fluctuations, but gravitational waves will only produce odd parity fluctuations. And so what one hopes to do is measure the even parity fluctuations accurately enough to determine the mass measurements, and then look for a residual that is left over that is unrelated to the distribution of mass, and infer from that how much of the polarization arises from an odd parity moment, and use that to hopefully infer the existence of gravitational waves from some primordial process. Now, what you're alluding to is the fact that about 5 years ago, there was a lot of hoopla because this was discovered. Unfortunately, what was left out is when we measure these things, other processes in nature produce different states of polarization. And so they incorrectly accounted for the effect of noise due to dust in our own galaxy. So what is happening now is, let me also emphasize, especially since I'm being recorded, that the team that did this measurement, they did an amazing job with the experiment. It is a beautiful measurement. They did a measurement of essentially the odd parity polarization at a level of precision that had never been done before. And so I think the fact that they unfortunately jumped the gun on their claims of its significance obscures what an incredible experimental achievement it was. They are now working with other teams that do a much more accurate accounting for what the dust contribution is. And that just turns into another source of foreground that must be measured and characterized simultaneously with the measurements that are being done. And so they have gone on, so that was of course the BICEP 2 experiment that made the premature claims. BICEP 3 is working with other teams that can measure the dust better. And their latest result is consistent with there being, they essentially now do not measure the effects of radiation, but they set bounds on it that are, they're getting better and better. To be perfectly blunt, this is one which I'm less optimistic about seeing in my lifetime, because it's a very difficult measurement to make. It would have huge implications if it were directly measured, but there's a lot of other things that are difficult to measure, and you just have to ask yourself, where do you want to put your time? This is not where I put my time personally.
20 years ago, it was your case almost that.
Absolutely.
Impossible.
Absolutely.
Now you say this is impossible.
I'm not saying it's impossible. I'm saying it's very difficult. I'm 48, and I say to myself, what do I want to see measured before I die? If I were a young person who is, say, 28, I might look at this and have a different point of view as to whether this was worth my time or not. If I were someone who was, it's all about where do you want to put your own personal time into doing these kinds of things, right? This is on the cusp, I think, of being measurable. The experimenters who are doing these measurements, they think that this may happen in the next 10 years. I don't know the technology as well. Maybe they're right, but I'm nervous because every time you improve sensitivity, you discover new noise. All right, let's take a little break then.